In this video, we are going to discuss Bayes' theorem. Bayes' theorem is used to determine uncertainty based on probabilities. It is given by this equation that you see right here. P of h given E is equal to P of E given h into P of h, the whole divided by P of E. You see two things here, h and E. E is evidence and h is hypothesis. So hypothesis is like your conclusion, and evidence is like your condition. So based on a certain evidence, you bring a certain conclusion. So these are like that. Now how do we prove this? Remove the relationship between conditional probabilities and joint probabilities. Now that would play a part here. Now we can also write this P of h given E as something like this. P of h and E divided by P of E. Right? Now we also know that the vice versa of this. P of E given h can also be written as P of E and h divided by P of h. Remember that h and E here are in the generic cases. That is, they are assumed to be dependent. If they are independent, then you wouldn't use the same form. So please try to contrast them. Anyway, you have P of E and h here and P of E and h here. So what you could do is you could combine this equation and this equation, and you can get something like this. And from this, you can finally determine your expression for Bayes' theorem, which is exactly this. So what does it say? It says that P of hypothesis given evidence is nothing but the probability of evidence given hypothesis multiplied by the probability of hypothesis, the whole divided by the probability of evidence. These probabilities here, they have a nomenclature associated with them. Like P of h is called as probability, P of h given E is called as posterior probability, P of E is called as evidence, P of E given h is called as conditional probability of E given h. So let us try understanding this better with the help of an example. Now this example is present in the textbook, so you guys might have already seen it, might have discussed in class as well, but anyway, let us have a look at it. So the question is this: Mike having cold has a probability of 0.25, Mike sneezing when he has cold is 0.9, Mike sneezing when he did not have cold is 0.2. So we need to find out the probability that Mike has cold given that he sneezes. So what is given in the question? That is what we are supposed to analyze now. Now, is Mike having cold the probability of hypothesis, or is it the probability of the evidence? Now how do we distinguish that? Now evidence is something that is present before we come at a conclusion. I told you that hypothesis is the conclusion, so evidence should happen before our hypothesis. So if you look at this entire scenario, sneezing is something that should happen before one realizes that someone has cold. So from this, what I can say is that cold should be my hypothesis. This should be my hypothesis. Now sneezing when he has cold, so sneeze here should be my evidence. So this is E given h. What is this? This is E given h dash, because this is Mike sneezing when he did not have cold. So this is E given h dash. Now what's our objective here? We are supposed to find the probability that Mike has cold given that he sneezes. So we are supposed to find the probability of h given E. Now here I might have used different symbols, but pretty much the picture is the same thing. So we have this 0.9 coming right from here. So this is our Bayes theorem, you guys remember. So this is P of S by C, which is nothing but P of E by H in this case, and this is P of H, a direct substitution. The problem comes with P of S. Now where do we get this P of S? So that's the $1,000,000 question. So what do we do for this is, If you guys remember the last lecture, we told you that an event can also be written as something like this. The probability of P of S can also be written as probability of S and C plus the probability of S and C dash. Okay, that's all fine. Now, what can we say about the probability of S and C? If S and C had been independent events, then the probability of S and C would be simply probability of S multiplied by probability of C. But over here, S and C are not independent events. The evidence and hypothesis are obviously linked, so we should not be using that formula. Instead, the probability of S and C will be written as the probability of S given C multiplied by the probability of C. So over here, the probability of S given C is 0.9, which is probability of E given H. That should be multiplied by the probability of H. So that is 0.25, which is this thing. Similarly, over here, this can be written as the probability of S given C dash multiplied by the probability of C dash. So in this case, it would be the probability of E given H dash. So it is this one multiplied by the probability of H dash. So we have probability of H as 0.25. So the probability of H dash should be 0.75. That is 1 minus 0.25. So you solve this entire thing, you would end up with 0.6. So you divide this with the denominator and then you do the entire calculation, you would end up with 0.04. So that is pretty much what you have with Bayes' theorem. Now we have an extension to Bayes' theorem as well. Not always do we have a single hypothesis and single event. We even have cases where you have one hypothesis and multiple events. So this is one such case. So over here, what we are trying to find out is the probability of a hypothesis given two evidences. Now you apply your basic Bayes theorem to it. What would you get? You get probability of E1 and E2 given H multiplied by probability of H divided by probability of E1 and E2. So that's pretty much basic. Now from this, we can develop multiple formulae. And one of the formula has been written here. So you can rewrite this as probability of E1 given H multiplied by probability of E2 given H into probability of H divided by probability of E1 and E2. Now this is right if the events are independent. If the events are not independent, then you cannot resort to this. So we have a few more forms here. So this is one of the form 1. Now this can also be derived from whatever we have seen here. So more about that later. And then you have few more forms here. This form 2. So you can rewrite the same thing as something like this. You can even rewrite the same thing as something like this. Now this is all fine, but then how do we even arrive at something like that? So for that, you just have to use a bit of your intelligence. So what you're supposed to be doing here is you tinker around with these values that you have here. So if you have, like, let's say, so this is what you basically have. So P of H given E1 and E2 can be written as P of H and E1 and E2 divided by P of E1 and E2. Now how are we getting this? Basically from the relationship between joint probability and conditional probability. So this is like the joint probability structure and this is like the conditional probability structure. And now I know I can expand this further. How can I rewrite this? I can rewrite this as P of E2 given H and E1. That is, I'm assuming that H and E1 have occurred before E2. So these become your evidences and this one becomes your hypothesis, sort of like that. So this is multiplied by this. So pretty much once again using your relationship between conditional probability and joint probability. So that is all you're doing here. And then you end up with an expression like this. So instead of considering H and E1 to be your evidences, you can even consider E1 and E2 to be your evidences. you end up getting a different formula. We could consider H and E2 to be your evidences. In that case, this P of H and E1 would be replaced by P of H and E2. So that again will give you a different formula. So it all depends on how you change your variables here.